When visualizing smooth particle hydrodynamic simulations, the underlying rendering method makes a significant difference to speed. While traditional scatter algorithms scale quadratically with pixel coverage, Py-SPHViewer 2 introduces a highly efficient alternative. By utilizing a hierarchical nested grid algorithm, Py-SPHViewer 2 completely decouples the time it takes to project the particles onto the scene from the desired final image resolution. This allows rendering massive particle datasets with constant numerical complexity, offering a scalable approach compared to other codes. In this short tutorial, we will see how to use Py-SPHViewer 2 to render the projected gas density distribution of a relatively large cosmological hydrodynamical simulation. For this example, we're going to use NumPy, Matplotlib, H5Py, and of course SPHViewer 2. We will also work with a simulation snapshot available at this link and listed in the description of the video. Let's go ahead and open up the snapshot. Today we're focusing on visualizing the gas density. This means we want to look at the data contained in part type 0. Let's load up the particle coordinates and split them out into separate one-dimensional x, y, and z arrays. Next, we need to pull out the particle masses, the box size of the simulation, and the smoothing lengths that the simulation already calculated for us. With these data in hand, we are ready to go. Before rendering the particles, we define three key arguments that control the desired resolution of the final image: the number of pixels used to sample the smoothing kernel of each particle, and the number of threads that SPHViewer will use. The final image resolution is controlled by the parameter Rmax. In SPHViewer 2, the resolution is always a power of 2, and Rmax represents that power. This means that setting Rmax to 10 tells the viewer that we want the final image to have 2 to the 10th pixels per side, which equals 1024. Secondly, the next parameter, cell per h, controls the desired number of pixels that the viewer will use to sample the smoothing kernel of each particle. Because the software uses nested grids of varying resolution, this value directly controls the rendering complexity. To avoid aliasing, setting this number to values typically greater than 4 is acceptable. Finally, because SPHViewer 2 can perform calculations in parallel, our ncores variable will control the number of threads we will ask the software to use. With these parameters set, we are now ready to call the render function of SPHViewer. This will return the final image, along with the physical extent used to map pixel units into physical units. The final image will have units of mass divided by pixel area, so that this is surface density. The unit of mass and length correspond to those of the particle coordinates and masses. Finally, we can plot the image as we would normally do. In this case, we are going to use Matplotlib's imshow function for that. To visualize the large dynamic range encoded in the image effectively, we plot the logarithm of the data. We also add a small constant value to the data before taking the log to avoid errors from zero values in any empty regions. Along with the image, we pass the extent array to ensure Matplotlib knows the correct mapping between pixel coordinates and simulation coordinates. For this example, SPHViewer 2 renders the full simulation box, consisting of more than 16 million particles, in under 300 milliseconds. It is important to note that the rendering time depends largely on two factors: the total number of particles and the number of cells used to sample the smoothing lengths. Interestingly, the time is not significantly affected by the final image resolution. This finalizes the QuickStart guide on using Py-SPHViewer 2 for your analysis workflow. For more information, be sure to check out these tutorials, which are also listed in the description of the video below. Thanks for watching.